Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part 1 of the Energy Basics segment. In part 1 we will discuss energy and power, kinetic and potential energy, and potential energy types. We will look into gravitational, electrostatic, and nuclear potential energy.
Let's first talk about energy. Here you see the sun. The sun is the primary source of all energy on Earth. Even if you're using fossil fuels, you can just look at it as solar energy stored in plants that then over millions of years became oil and coal and so forth. Here's that energy flow chart again. In the sense of the energy basics segment, what I would like to point out on this chart is that we essentially put potential energy into the system. So these are things like coal and oil and gas and biomass and nuclear energy. So this potential energy is fed into the system, and then we convert it for uses to kinetic energy and or heat. And then once we're done with everything, once the cars have stopped in the parking lot and the oven has cooled down and so forth, all that energy that we put in here from these potential energy sources has been converted to low-grade heat that has been dispersed to the environment. It's interesting to point out at this point that there is no way, no straightforward way to take this low-grade heat and convert it back into these potential energy types so that we could close the loop. So in essence, nature always works in a way that high quality energy is being converted to work, and then it is dispensed as low grade energy into the environment. The amount of energy remains constant. It's just that the quality of energy changes from high quality sources to a low quality source, which is not useful. On this slide, I want to define energy, work, and heat. Now, energy is a property of bodies, and the amount of energy is constant in the universe. So that means we can only transfer energy from one body to another, but we can never make energy or destroy energy. When we transfer energy between bodies, there are two ways to do it. One is that one body does work on the other body, or the other is that one body transfers heat to the other. These are the only two ways to transfer energy from one body to another. Work and energy have the same units, so if you apply a certain amount of work on something, then you transfer an equal amount of energy to that body from your own body. So let's examine a typical example. Imagine you are pushing a shopping cart, symbolized by this green rectangle, and so you apply 100 newtons force over a distance of 5 meters. So you accelerate it from 0 to a certain speed over 5 meters applying this force, then you would have done an amount of work on that shopping cart that is equivalent to the force that you applied times the distance. So if you apply 100 newtons force, then it would be 500 joules of work. That would mean that in absence of friction, this shopping cart would, after this effort, would have a kinetic energy of 500 joules. So what's happening in terms of energy transfer? So this white rectangle, that is you, and I put a Snicker bar in your stomach, and so there's a certain amount of chemical energy in it. And so as you start working on this shopping cart, then you transfer an amount of heat to the environment. So you start sweating a little, and heat is being transferred to the air molecules around you. This is typically about 75%, so your efficiency to perform work is about 25%, very similar to a gasoline engine actually. And so these 25% of work now, they are being converted to kinetic energy of this shopping cart. So the Snicker bar transferred energy to you, and then you transferred energy to the environment, and a little bit of that energy that came from the Snicker bar is being transferred to the shopping cart that has a certain kinetic energy after your effort that is equivalent to the work that you performed on it, if we assume that there is no friction. So let's summarize what we need to remember for the remainder of this segment. Energy is constant. Energy can only be transferred between bodies. Work and heat are the only ways to exchange energy between bodies. and work and energy have the same units. So if you perform work on an object, then this object will have that work equivalent energy after your effort. So in this example here, the Snicker bar, the atoms in the Snicker bar, they converted some of the chemical energy to heat and muscle contractions, and then you were able to perform some work, and this work turned into kinetic energy of the object. Let's talk about energy units. Unfortunately, there is quite a few of different units in use. You may remember when you look at your energy bill at home, there is the kilowatt hour on there. So you pay, what, 10 to 20 cents per kilowatt hour. The meter kilogram second unit, the scientific unit, is joule. 1 joule, you basically saw it on the previous slide, is the work done when a force of 1 Newton moves the point of its application a distance of 1 meter. So if you would push the object 1 meter at 1 Newton, then you would have imparted 1 joule of energy onto that object. Or you could say you would have done 1 joule of work on the object. So 1 kilowatt hour is 3.6 million joules. So you see the difference. Joule is a very small energy unit, while kilowatt hour is something that is easy to use for human energy use related applications. Some other energy units that are being used, when you look at your Snickers bar, there is the calories. There are calories on there. However, the food calories, they're really kilocalories, so 1,000 calories. So 1 calorie is 4.18 joules, so it's a very similar unit in magnitude. It's just not part of the MKS system. Then there is the British thermal unit. Even though it is a non-metric unit, it translates conveniently into 1 kilojoule approximately. Then we have tons of TNT. That's the energy in explosives typically. So here we have 4 times 10 to the 9 joules, 4.18 gigajoules in 1 ton of TNT. And then, of course, when it comes to fossil fuel liquids, the barrel. And so a barrel has 159 liters of crude oil, 42 gallons, and the energy in there is 6.1 gigajoules. There's another interesting unit that is used when you look at chemical reactions and things like that, and particle physics. It's the electron volt. So that's the energy, the kinetic energy of an electron that was accelerated by a 1 volt potential difference. And this 1 electron volt, that is 1.6 times 10 to the minus 19 joules. So you see this is a really, really small unit, much, much smaller than the joule that we thought already was pretty small. And so this small amount of energy, that is convenient when you think about the energy that is coming from chemical reactions. You can say that an individual chemical bond, when that forms, has typically energies of 1 or 2 electron volts that are being released if it is an exothermal reaction. So every time you react a gasoline molecule with a few oxygen molecules, then you get a few tens of electron volts out of this reaction. Okay, now we know what energy is. Let's have a look at power. What is power? Power is energy conversion per time. So if something has a higher power, it means it can convert more energy from one type into the other, or it can perform more work. So really power gives us the rate of energy conversion or the rate of transfer of energy to other bodies. For a power plant, that means if it has a certain power output, right? You may have read something like a 1 gigawatt power plant or so. This is a large power plant, has 1 gigawatt. So what does that mean? This power plant is able to convert as much coal as it is needed to put out 1 gigawatt of power. So how much energy is that per day? Well, power is energy per time. So if we multiply the power with the time, then we know how much energy came out of this plant in that amount, in that length of time. If we have a 1 gigawatt power plant and we wait 24 hours, we let it run for 24 hours, then we would have converted as much coal to produce 24 gigawatt hours of energy at the output here. If you want it in joules, then that would be 86.4 terajoules, because one day has 86,400 seconds. The unit of power is the watt, and watt consequentially is of course joules per second. So if you want to calculate the joules, you just multiply the power with the seconds that whatever runs at that certain power. As an example, the average residential house uses 30 kilowatt hours per day. That's 2008 data from the Energy Information Administration. How much power plant do we need to provide this average energy per day? So this means in the entire day the house is consuming 30 kilowatt hours on average. So if we wanted to provide this energy now, what is the power that we need in a power plant? Well, we have 30 kilowatt hours per day, so if we divide that by 24 hours, we get 1.2 kilowatt. So a 1.2 kilowatt share of this power plant would be needed to provide the energy for one house. So if we have a major power plant of 1 gigawatt, then that means, if we divide by this here, that means that we can supply the energy to about 800,000 homes. As a real-life example, let's look at the Tampa Bay area. Here we have three major power plants, TECO power stations in Big Bend and Bayside. They have each about 2 gigawatts, and then we have the Progress Energy plant in Crystal River, which after closing the nuclear plant still has 2.2 gigawatts. So we have about 6 gigawatts for Tampa Bay for 4 million residents. So that means we have about 1.5 kilowatts per resident. Let's look at some magnitudes of power around us. If you look at the average human, he or she has 100 watts. If you consider that there's only 25% efficiency of converting energy into work, then we have a work output of about 25 watts. And this is just a small old incandescent light bulb. So this makes immediately clear that for our lifestyle we need machines around us that have a much higher energy conversion rate or power. So if you look at power stations, the biggest one that we have right now is 18 gigawatts. That is the Three Gorges Dam, which is the world's largest hydroelectric power plant. Then if you look at the total installed wind turbine capacity at the end of 2006, that was 74 gigawatts. That may have doubled by now. If you look at the first stage of a Saturn V rocket, that has 190 gigawatts, so 190 major power plants, pretty amazing. The burn time was 168 seconds and the rocket went up 67 kilometers. So if you compare this energy expenditure over these 168 seconds, that's the energy that's in about 30 million Snicker bars. It takes about 15 minutes of power workout to burn 250 kilocalories. And so at a 25% efficiency at doing work or lifting a rocket, one person would have to work hard for about 30 million hours or 3,424 years to get that rocket onto that 67 kilometer height. That's pretty powerful, this rocket. If you look at the total energy conversion rate in the US in 2005, that was 3.3 terawatts. That compares to 16 terawatts of the total human power use in 2010. So it's about 20% of that happens in the US. The heat flux from the Earth's interior is 44 terawatts. The global biomass production via photosynthesis runs at 75 terawatts. So you see that the energy coming from the Earth's interior and the biomass that's being produced, or the rate of biomass production, is in the same magnitude as the global power use. And so that tells us immediately that it will be difficult to use these low density resources to actually cover this power need. We need to find sources that have a higher power output. Finally, if we look at a hurricane, So the rate of heat energy released by a hurricane, that is 50 to 200 terawatts. That tells us that most of the energy that's coming from the sun is actually going into heat, and very little of that is going into biomass production. Now we know that it's all about energy conversion. I showed you at the beginning the energy flow diagram of the United States, and there I said that we start out with potential energy and then we convert that to kinetic energy. We distinguish between three types of potential energy: gravitational, electrostatic, and nuclear. So when you think of the potential energy inputs of the US energy system, gravitational, that is essentially hydroelectric dams. We collect water at an altitude and then we let it drop through a turbine, so we extract gravitational potential energy. Electrostatic potential energy, this is typically what's coming out of chemical reactions. So when you burn fossil fuels, this is essentially the potential energy that is being converted to kinetic energy. And if we think of nuclear, of course, that is what happens during fission or fusion in nuclear power plants. At this point, there are only fission nuclear power plants in use. Kinetic energy is related to the velocity of objects, and so we distinguish between the collective motion of all atoms in an object. So this is just what we typically think of kinetic energy of an object when we accelerate a car, for example. And then we have the individual motion of all of the atoms inside an object, and that is called heat. So heat is the added up microscopic kinetic energies of each of the atoms inside an object. Kinetic is usually what we want, so we use potential energy and then we convert it into kinetic energy. The classic example is we have a rock at a certain height above ground, and so it has a certain amount of potential energy, and then we drop that rock, and as it falls, it converts this potential energy into kinetic energy. And then, of course, once it hits ground, this kinetic energy is then being converted into heat, and then the process is over. And so, in other words, we can say that the potential energy change results in a transformation to kinetic energy. And there's a simple formula for the kinetic energy. If we know the velocity, then the kinetic energy is just 1/2 times the mass of the object times the velocity squared. When it comes to potential energy corresponds to the work that was done to an object against a force over a distance r. And of course, forces we always have between two objects. So if we separate two objects, then we store potential energy in them. And if we let them get closer together, then some of this potential energy is being released, and the energy state of these two objects is lower after that, and the released energy that was transformed into heat or kinetic energy. So an example is if we shoot up a rocket into space, then we work against the force between the rocket and the Earth. And the formula is proportional to 1 over r squared. So here's the gravitational force. It's minus gravitational constant multiplied with the two masses. m1 would be Earth, m2 would be the rocket, and then divided by the distance squared. And so this gives us a curve like this. And if we plot the energy here on the y-axis, if we separate the rocket from the Earth, we have to work our way up this curve. And so this is what we're really doing. We do work on the rocket by means of the powerful rocket engines, and thereby we move the rocket along this curve. And so the energy goes up, the potential energy. Now if the rocket is outside here, then we can turn off the engines and we can let the rocket fall back to the Earth. And so it will regain all that velocity that was expended in getting it out into orbit. As the rocket falls back, the potential energy that it has here, that will be converted back into kinetic energy. So it will accelerate and get faster and faster as it falls back to Earth. If we talk about potential energy between particles, usually we don't use the word potential energy, we use the word binding energy. But in essence, it's exactly the same. If we have a chemical reaction between two particles, they are initially far apart, and then when they find each other and they do the chemical reaction, they get closer and the potential energy gets lowered and the kinetic energy of the particles gets bigger, and that then results in a increase of the heat typically in that chemical reaction volume. So again, we convert potential energy, that in that case has to do with electrostatic attraction between the atoms. We convert that potential energy into kinetic energy, which manifests itself as heat. We know now there are three principal types of potential energy that depends on the three different forces that are acting in nature. We have potential energy that comes from gravitational interaction between two bodies. We have potential energy that comes from electrostatic interaction. And we have potential energy that comes from the strong nuclear force. It's difficult to compare these energies. It's a little bit like apples and oranges. But if we look at the principal strengths of the individual forces, we can, I think, immediately tell which forces lead to more potential energy density. If you consider two carbon ions that are singly charged, so one electron missing or added per carbon atom, so if we put these two carbon ions at a certain distance, the electrostatic forces between them are 10 to the 40 times larger than the gravitational interaction between them. That immediately tells you that electrostatic forces are much, much stronger than gravitational forces, and that would of course mean that the electrostatic potential energy between two carbon ions is much stronger than the gravitational potential energy. Now the nuclear strong forces between the nucleons, they only act over very short distances, but when they act, they are several magnitudes stronger than electrostatic forces. And this is easily obvious because they keep the positively charged protons in the nucleus from repulsing each other. So the consequence of all this is that the potential energy stored in matter is mostly nuclear, a little bit is electrostatic, and this is what nature and chemistry essentially lives on, and a very small amount is gravitational. We only see gravitational forces strongly because the Earth is so big, and so we get sizable forces. These potential energy magnitudes differences are immediately evident in the amount of fuel that is being used in nuclear reactors, conventional fossil fuel power plants, and hydroelectric power plants. If you look at nuclear reactors, they need once or twice a year a few tons of fuel rods, while if you have a conventional fossil fuel power plants or coal-fired power plants, continuously trains are being unloaded and coal is being shoveled into the boilers. Several more magnitudes of fuels go into a hydroelectric power station. There we have an entire lake that is being fed through the turbines. Now let's look at how we can convert some of that potential energy. Let's start out with gravitational potential energy. Gravitational potential energy is pretty much exclusively used in hydroelectric plants. The principle is simple. All we have to do is put a dam in a river that leads to a rise of the water level, and then we get water at a certain altitude, and this we can use by letting it drain down through a penstock into a turbine into a lower level downstream outlet. This turbine drives a generator, and so we get some electrical power out of the gravitational potential energy that is stored in the water above this intake. It is a little bit more involved to understand how we can convert electrostatic potential energy, because charges are typically found on atoms. Therefore, we have to deal with chemistry if we want to extract the potential energy between those charges. Let's look at the potential energy of electrons within atoms. In a simplistic way, we can look at electrons in an atom as electrons going on orbits around the positive nucleus. and they're being kept on this orbit by attractive electrostatic forces. A little bit similar to planets going around the sun, and they are being held on their orbit by gravitational forces. The only thing that is different to the planets around the sun picture is that electrons can only go at certain distances from the nucleus. So we have discrete allowed orbits that can be inhabited by these electrons. They cannot be in between these orbits. This is a consequence of quantum mechanics, and it is beyond the scope of this course. So at this point, let's just believe that this is true. Here on the right you see a graph that links the distance of an electron to the nucleus with the potential energy. And so similar to the gravitational case, as we go further away from the nucleus, the potential energy gets larger. If we can move an electron from further out to closer into the nucleus, we can extract the difference of the potential energy. Typically that is being released as heat or as light, as a photon. E1, 2 to En, these are these discrete energy states that correspond to these different orbits. So we can only have jumps between those energy levels. So how can we extract potential energy from atoms? The solution to that is making molecules. If we look at a covalent bond, which is shown schematically here, we have the individual atoms. So these two atoms now are supposed to combine in a molecule. And what happens is the two atoms, they get closer together. And since the nuclei repulse each other, the electrons need to go in between and form sort of a neutralizing area that is negatively charged. And so like glue, these two electrons now keep those two nuclei together. And so this enables the formation of a molecule. In terms of energy states, what happens is that we go from individual energy levels on the atom. So these are one of the orbitals that we just saw on the previous slide. And after the molecule forms, we get new electronic states. Typically we get a so-called bonding electronic state and an anti-bonding electronic state out of these two electronic states of the individual atoms. Now once the bonding and anti-bonding states are formed, the electrons on the atomic states, they of course go to the lower energy level. The difference between the potential energy on the individual atoms and the potential energy on the bonding states of the molecule, this difference delta E, that is being released. Since we have two electrons, we get actually 2 times delta E out of this reaction. This is the source for the heat that is coming out of chemical reactions. So let's look at an example, burning fossil fuels. Here we have a stick and ball model of an octane molecule. Octane is a typical molecule found in gasoline. It is C8H18, so we have 18 hydrogen atoms and 8 carbon atoms here in the backbone. If we combust this now in the combustion chamber of a car, then we have this chemical reaction that is going on. So we take 2 of these octane molecules and we add 25 oxygen molecules, and that gives us 16 carbon dioxide molecules and 18 water molecules. Let's examine now what happens to the carbon and oxygen atomic energy levels. They are shown here when carbon and oxygen are combining to carbon dioxide. And here in the center we see the carbon dioxide molecular orbitals, the bonding molecular orbitals. And what we see is that the bonding states of the carbon dioxide, they are lower than the atomic energy levels of the individual carbon and oxygen atoms. And so after the molecule forms, we have lower lying states that take some of the electrons that are in these higher lying atomic electronic orbitals. This is the energy difference here and there that is coming out of this reaction. So this is an exothermic reaction, and heat is being released when carbon and oxygen make carbon dioxide. A similar diagram could be drawn for hydrogen and oxygen, the second part of that reaction when water is being formed. Let's find out how much energy is being released from typical fossil fuel combustion reactions. This slide shows the numbers for the combustion of methane CH4, natural gas. The chemical equation is shown here for this reaction. So we have one methane molecule and two oxygen molecules, and that gives us one carbon dioxide molecule and two water molecules. Now, if we want to know how much heat is coming out of this reaction, we need to look up the binding energies of the reaction partners. There are tables for that, and in these tables, the binding energy for oxygen is typically set to 0, and then everything else is relative to that. So this makes this very simple. All we need now to know is the binding energy of methane, and we know the energy that is going into this reaction. So we have minus 75. And this is in kilojoule per mole. Now we need to look up what the binding energy is for the reaction products, and the table tells us for carbon dioxide we get minus 394, so it's considerably lower than 75. So that clearly shows us this is the more stable reaction end product, and this is the molecule that contains energy. Similarly, for water we get minus 242. To balance this equation, we need to add the heat that is coming out of the reaction. If we solve this for heat, then we can directly calculate the heat that's coming out, and we get 803 kilojoule per mole. Now, if we consider the weight of methane per mole, which is 0.016 kilograms per mole, we can calculate how much heat is in a kilogram of methane when we react it with oxygen. And that gives us 50 megajoules per kilogram. So this is the energy that comes out if we react 1 kilogram of methane with the appropriate amount of oxygen. In kilowatt hours, this is 13 kilowatt hours heat per kilogram. Remember that the average house uses about 30 kilowatt hours per day. If we assume that this is just for heating, this would mean that you would have to burn about 2.5 kilograms of methane to heat that house with 30 kilowatt hours. So how can this process be reversed? How can we get the electrons from the lower energy states back into the higher energy states? In essence, how can we make fossil fuels again out of carbon dioxide and water? Well, nature has the answer. Remember that fossil fuels in the first place are a product of photosynthesis. In essence, these are plants that grew millions of years ago that then over time with pressure and heat turned into fossil fuels, and now we're burning them. Photosynthesis is the way to generate more fossil fuels out of carbon dioxide and water. Plants do this in chloroplasts. If one shines light on a chloroplast and offers carbon dioxide and water, the water is being split into oxygen and hydrogen, or rather hydrogen ions, protons. And these protons in a secondary process, this Kelvin cycle, transform carbon dioxide into sucrose molecules that come out of this reaction. Down here is the chemical equation. 6 carbon dioxide and 6 water molecules plus light turn into sucrose and 6 oxygen molecules. And so a hydrocarbon chain has been generated from water and carbon dioxide with help from light, or I should rather say with energy from light. Now we understand how to extract electrostatic potential energy from molecules, so that explains how we can convert fossil fuels into heat or kinetic energy. There are also other forms of electrostatic potential energy that are in use. I should mention the electrical power plants. So in an electrical power plant, a generator uses induction to move electrons in a conductor from one side to the other, essentially, and that generates an electrostatic potential difference across this conductor, and that can be used to power a load. So this potential energy difference is known as voltage. If you look at batteries, they are essentially devices that harness chemical reactions between ionic compounds. Instead of just releasing the energy as heat within the reaction product, the exchange of the electrons from the higher to the lower energy level, that occurs through the wire that connects the load to the battery. So in summary, we have a chemical reaction where electrons go from a higher to a lower energy state, but on the way there they have to go through the wire and the load, and that allows us to extract the potential energy from chemical reactions as an electrical current. If you look at solar cells, they are similar to photosynthesis. So here we use photons to increase the potential energy of electrons. Essentially, we move them from a lower energy state into a higher energy state with photons. This potential energy difference is equal to the photovoltage that we get out of a solar cell, and this can be used to generate a photocurrent through a load. Finally, let's discuss how to convert nuclear potential energy. And again, like with electrostatic potential energy, it is all about the binding energy difference between reactants and reaction products. What is shown here is the prototypical fusion reaction. In fusion, one uses tritium and deuterium, two hydrogen isotopes, one with one additional neutron and the other one with two additional neutrons, and we react them into a helium. So helium is the reaction product and a neutron and some energy. Now energy is being released because the binding energy of the nucleus of helium is lower than the binding energies of the nuclei of deuterium and tritium. This graph plots the average binding energy per nucleon versus the number of nucleons in the nucleus. So on this end here we have the small atoms, and over here we have the large ones. Now this scale unfortunately has the opposite sign than the scale that I introduced for the potential energy of electrons in atoms. So when you interpret this graph, keep in mind that the largest potential energy is down here at 0 and the smallest potential energy is up here at 9. And so if we go from 0 to 9, we would actually release energy. Now, when you look at this graph, it has a maximum, and this maximum is at iron 56. So this is the atom that has the smallest potential energy in the nucleus. When it comes to extracting potential energy from nucleons, then we have two ways to do it. Either we can take small atoms or small nuclei and fuse them together and go and march towards the iron 56, or we can take big nuclei like those in uranium-235 and fission them into smaller nuclei that are closer to the iron 56. Both of these processes will release energy, right? Because we go from something with a higher potential energy to something with a lower potential energy that's closer to iron. Same on this side. So what I just showed you on the previous slide was to take a deuterium and a tritium and make helium out of it. So we get this difference essentially as energy output from the reaction between these two nuclei. If you take a uranium-235 and you shoot a neutron at it and fission it, here in the example it's cerium 140 and rubidium 93, then you would get the energy difference between this point and the 2 points for these isotopes here on the curve. Okay, so we have fusion and fission, and we can take nuclei and then drive them towards iron, which has the lowest potential energy. So this is the energy that we can get out of these reactions. Now, one little detail I didn't talk about yet, the energy scale that we have here. If you look here, this is mega electron volts. So I told you earlier that the typical chemical reaction gives you 1 or 2 single electron volts. Here we have millions of electron volts. So if we go from deuterium to helium, we get actually almost 2 million electron volts out of the reaction of 2 nuclei. Think of that. So this single reaction between 2 nuclei releases the same amount of energy like a million chemical reactions. So this here immediately explains to you why there is so little fuel needed in a nuclear power plant compared to a fossil fuel power plant.
This concludes part 1 of the Energy Basics segment. Thanks for watching.